Okay, so I wanted to just show you a little bit about how I might forecast a chase position and a little bit how a meteorologist might approach a complicated situation like this. Anytime a meteorologist is making a forecast, the first thing we're really going to look at is the water vapor loop. So this is a current image from space, and what we're doing is we're taking a picture of where the water vapor in the atmosphere is. We want to know where there's more and less concentration of water in the atmosphere. And these really bright colors, those are thunderstorms and clouds, but there's more opaque color in here. That's just water vapor. And then there's this dry area right here. You can see it kind of loops down and seems to join up. And this is actually the jet stream. That's what we're really looking for. The meteorologist in me quickly picks up the fact there's this bend in this clear area. And I see that as a developing storm very easily. And actually, I can pick out some nice characteristics of that in this image. But for now, I want to just look and see, like, do other maps support that there's kind of a dip in the jet stream in here? So what I do is take a look at the most recent model diagnosis of the wind speeds up at the jet stream level. And sure enough, here it is. You can see this jet stream dipping down through, the Southern California, Arizona area and back. You can see there's a relative maximum of wind speeds in here, just over 100 knots. And that's going to kind of rotate around that corner of the base, just like you were seeing those clear air in that water vapor image. And that's our storm right there, that jet streak rotating around the bottom of this trough. That's actually what's going to make the weather happen. And so the first thing I might do as a forecaster is say, well, what's that going to actually look like over time? So let me pull it forward here using NAM, and you can see that jet streak rotates around and ejects out the bottom and does some pretty interesting stuff over the next, 36-ish hours. This is really a picture here that's going to tell the biggest story. You can see how the air is spreading out. We call this diffluence. And this diffluence downstream of the jet, that's what's going to spread out aloft, and that's going to make a hole that the air at the surface needs to rise to fill. And that's actually going to be augmented by the fact you've got this faster wind speed here, some fluid dynamics to explain why this area kind of that I'm highlighting right now is going to see enhanced synoptic lift. The weather is already prone to be rising, even not considering convective, not considering kind of just buoyancy things. And so what I'm going to do is see, well, is there any rotation in those levels that might help me get a low? And we're going to look at vorticity to do that. And so now we're stepping down in the atmosphere. We start off right at the top of the troposphere. Now we're down in the middle of it, around 500 millibar. And this map shows me the twist in the air. It's called vorticity, and it's a bit colorful and hard to read. But I want to point out, as you can actually see, there's a couple maximum of vorticity here. One over like southern Wyoming, the other over like, let's say, Albuquerque. And as those eject out, they're kind of interacting with each other. So the Rockies have something to do with that there. And it's a bit complicated, but I would just say, for now, I see this big trough swooping down. And there's this energy within that trough at the mid-level. And that's enough for you to understand more or less what's going on for the moment. And my question is, does that energy make it down to the surface? Do we see any rotation at the surface? And of course the answer is yes in this case. We can see big southerly winds coming up from the Gulf. Then you can see some winds running along a boundary here to the east. And if we come farther forward, oh, there we go. Here's our low pretty clearly. Winds up, winds down, some kind of a boundary through here. Look at the temperature gradient. That's quite impressive. Another like warm front through here maybe. Hard to tell on a first glance what's going on here if you maybe aren't trained to it. On the other hand, there's clearly, and then here comes the day, clearly quite a bit of a rotation at the surface there. And so what I'm going to do is use a map called theta E. And what I'm really looking at here is a map of like the temperature and humidity combined. And understanding exactly what's going on here isn't important. What I want you to see is basically that there are sharp lines on here. So let's pull this forward into the future. Okay, 12Z. This is going to be like 6 in the morning. All right, here we have some really low theta E air and some high theta E air and a really sharp gradient between them. So this has got to be like a dry line or a cold front. That's the only thing that can do that. There's like a notch here. Okay, that's our low, and you can actually see the spin in the wind barbs here. And horizontally, that's going to be our warm front. So we got a warm front stretching down, and a dry line or a cold front or something coming down over here. And in between, we've got a low kind of driving those rotations. And as the day goes on, it heats up, and you can see that heating up creates some really high theta E air here across like Wichita to Salina, Kansas. You see this purple right here, right in front of this kind of bold shape. The one thing to note as a meteorologist is all the winds are southerly on both sides of the dry line. We don't really want that to be the case. We'd rather see these kind of abutting at kind of more westerly, but that's something we'll talk about in a bit. Now that high theta year starts off as thunderstorms, and it actually dissipates pretty fast. You can see as it goes night, we get cold, and the dry line marches on to Wednesday, which actually may be a second severe weather event, although not as significant. We can check and prove it's a dry line by just looking at dew points. So this is just the moisture in the atmosphere. You can see here it is right now. Pull it forward into the future. Okay, this is 18Z. This is about noon. Got my low sitting out here. Real sharp gradient of moisture. And a warm front, obviously not as formed. And you can actually see there's this big rising area here. So you can see this moisture is being pulled up this way around the low, shoved up over that warm front. You get some overrunning. You're obviously going to get some convection in that area and some more mechanical forcing along the dry line itself. And the dry line's a bit wavy, which tends to be a good sign for initiation. So you keep stretching it forward, and you can get this really nice bulge across central Kansas. Kind of here again, that Salina to Wichita area. You can see how that's kind of on the cusp of this bulge at 21. And at 0Z at 6 p.m., the dry line actually seems to almost stall and then retrograde, but really get sharp here. And that might be a result of the actual thunderstorm starting to form. Kind of moving down the line here really fast. Next question is, well, how unstable is air going to be? Okay, I've got heat, I've got moisture, but is there actually any ingredient here that's going to cause lift? And so I look at CAPE, which is just a measure of how likely the air is to have energy in it. And let's just pull it forward to kind of peak time. Okay, so here we are. This is kind of the biggest picture, and you can see we're getting a peak CAPE here along, again, that Wichita to Salina area. So you see I'm starting to narrow down this area. And that peak CAPE is about 5,400 joules. And just speaking from experience, in early to mid-April, 5,400 joules is pretty rare. This is a really energetic storm for this time of year. I would put this towards the category of high to even extreme instability. This area has a lot of thermodynamic energy waiting to be liberated. And underneath that whole trough and that synoptic lift, that is going to come out pretty energetically. And so I can say, well, okay, yeah, I've got a lot of air rising, but is it going to twist? And so I take that EHI and I multiply it by helicity and see kind of where's the area the air is most likely to twist and rise at the same time. And so what I'm looking for is just the brightest colors here that fit my other criteria too. Like, okay, yeah, there's some really high EHI here, but that doesn't mean anything to me unless I know that those storms are going to form. So you stretch it off, and yeah, okay, this is huge EHI, but it's also at midnight. Okay, so we're going to let that go. Okay, now 15Z, now we're getting closer. 18Z, okay, 18Z, we're looking like close to when school dismisses. 21Z, okay, getting closer. Okay, 6 p.m. Whoa, what are those holes? This looks good, this looks logical, but okay, these are thunderstorms that the model's starting to render. So it's saying, wow, the thunderstorms aren't actually going to form maybe right on that boundary. They're going to form a little off in front of it. So let's look at the run right before they form. Okay, we got this like local maximum where, okay, the highest instability was, which is kind of contaminating our twist measurement, right? Got this bulge in Nebraska, maybe up to Omaha and Grand Island. But again, this kind of North Concordia to Salina area seems to maximize at this value. We don't want to get too bogged down in that, but let's start there. Okay, so far we've only been using the NAM, and there's actually a whole lot of other models. So here's the GFS rendering the same thing, and you say, ah, look, there it is. This looks pretty familiar. No. What's this doing over Kansas City? Like, the maximum was over Salina, and here it's over. That makes almost no sense. If I look at the precipitation map, well, actually, yeah. Yeah, here it comes. So what it's doing is it's moving this dry line through faster than the NAM. If this is to be believed, at 6 p.m. we have a line of really strong thunderstorms pretty much encroaching directly on the metropolitan area. We've got them running from St. Joseph down here through the 169 corridor. Like, we're past Wichita already. Okay, if this is to believe, then we got to just chase really close to Kansas City. And we got to move this whole thing over. Now, for several reasons, I'm not exactly sold this is going to be the case, but something that be cognizant of. If I see the dry line marching forward faster tomorrow, then I know that I have to move my target into line with this. And there's some pretty impressive values in here. So with that in mind, I might say, okay, well, that's what the GFS says, but what does the NAM say that precipitation is going to form? So we'll move it forward. There's some cloud cover that's being rendered here. Here's that same time. This is not really an impressive picture on this particular model. You see, well, okay, here's Russell, Salina, Chanute. This doesn't really tell me much. I have to kind of drag it forward a little bit more before I get this line here at almost 9 p.m. This is not a very favorable picture to me as a chaser because it's after sunset, it's messy. It's hard for me to figure out exactly what's happening in this picture. Okay, there's a low kind of in here twisting stuff around, but geez, that's a mess. I don't really want to even have to deal with that. Yeah, no. But of course there's some hope. So let's take a look at this. So let's come into an even higher resolution model. So we're just going to keep looking at these simulated radars. And these aren't the best forecast tools, but they're really easy to understand. And that's why I'm going to choose them for a while. Okay, this one shows some thunderstorms actually forming overnight here by St. Joseph. And they actually do something really interesting, which is they get stuck on that warm front as it lifts north. So here's that warm front lifting north. And this is, again, 2 in the morning. This is coming up pretty fast right now. You actually see those thunderstorms kind of stick on that warm front and come right through the metro area. Here we're at 14Z. So 14Z, that's like 8 a.m. This is actually quite a big thunderstorm. If this were to verify, we're talking severe thunderstorm warnings, even possibly a tornado warning, to be completely honest. Definitely a watch. If this actually were to verify it, it is quite possible. We actually may see some very strong thunderstorms early in the day. And this is what I actually want to draw your attention to. This is actually the forecast challenge today, is how this guy works. Because you see, I draw him through, and he moves out. And this model shows those cloud covers. And here we go. At 20Z, we've got a thunderstorm starting to form. 21, ooh, it's getting pretty nice. 22, 23, now we see some supercells firing up right along that dry line where we expected it from the other NAM models. 23, 24, 0Z, 6 p.m. We're kind of at the peak. And actually, if you've noticed, Kansas City here has been pretty wet all day, pretty active thunderstorms. Actually, really an interesting pattern there, too. I just think the energy there might not be quite enough to support the strongest of the severe weather. That's why I probably would head west. Being said, I'd be perfectly comfortable sitting here in the sea. Something interesting would happen if this model is going to verify. Very quickly, I'm going to look at the track these storms take, and I'm just going to say, well, where's the most intense rotation tracking? And just drag that forward. Okay, here we come. Those morning thunderstorms starting to latch the warm front. And actually, they sit down some pretty impressive values for this measure. So again, I would expect a severe thunderstorm watch if this is actually starts to happen or show that it might happen. And here come those storms forming. Okay, we can see they're actually moving pretty much due north. So you can see they start off here just south of Salina. So this would be like, I've forgotten the name of the town here, but it will move north, cross I-70 and keep moving north. And yeah, that's pretty much the cell of the day, actually. You got these supercells that form way south here towards Medicine Lodge. Not particularly interesting to me because that's a long drive compared to this. So then I got to drive back, and here I can kind of make a loop. Storms come out, and there we are. Quite an active event, maybe even after sunset. Now what I'm going to do is actually show you our newest tools. This is the same exact model you just looked at, just zoomed in really tight on Kansas. So there go those thunderstorms in the morning. Here comes that first thunderstorm initiation, and this is the 0Z. And you can see really a better picture that we think the main initiation is going to happen. Here's Salina, here's Manhattan. Okay, so between there, it's Junction City then, and just north of Junction City. You can see that area really does seem to be most active. Let me pull it through. We do have this kind of spattering pockets of maybe supercell, convection, messy. We don't really know what's going on in this picture. But hey, it congeals into a nice line. And by 6Z, by almost midnight, we're still looking at possibly quite strong thunderstorms in this area. Looks like I may pull up a sounding here, which I don't need, so I'm going to move down. Yeah, even here, we're still looking impossible. Now, the last thing I want to consider is those thunderstorms over Kansas City, because they're actually kind of the wild card here. So this is a really nice map of temperatures. As I draw it forward, you can see the nighttime and the temperatures cooling off. I think you should see in here these dots. Those are lakes. Okay, so we drag that forward, and these models are very high resolution, very impressive. And here go those thunderstorms. Real soon. There they are. You can see that cold air here spreading as that thunderstorm moves forward, and the really warm air. So you get this like mesoscale boundary through here, this outflow, this rain-cooled air. You got the active thunderstorm front here. Some really hot air here. The dry line's probably running right about here because you can see this wind shift. So, you know, I'm watching right in here for development without any hints. And let's just move it forward a little bit and see if that happens. Still watching in here maybe. See some like cloud cover starting to show up in the radar here. Really, this rippling outflow shows me that this area is ripe for development. Moving it forward one more time, and voila, there the thunderstorms come. You can see them putting down their cold air. And there we see really the key story. Whatever thunderstorm fires first is going to get this really nice, juicy air. And my concern is if I target up here, I might be still chasing in the wake of the thunderstorm state. You see, this energy is not pulling in this really nice, warm, moist, unprocessed air. It's starting to pull in air that's already been used by a thunderstorm. So really, when I'm in here, I'm looking and saying, okay, I might want to target a little farther south than the model says the bright area, because that might give me the best spot for the thunderstorms to first fire off, because there's this wake of this nice cold air coming in. Plus, it's got this nice flow of air from the south. So it's got energy to deal with. Plus, it's got this thing going on to help it fire off. So that might move my target a little bit farther south. And I'm just going to check that against the moisture really fast. And you can see that moisture surge far north and then start to get eaten a little bit. Here's our thunderstorms forming over in the morning thunderstorms. These are the ones in the morning. These aren't the main severe event. And you can see it's actually taking the moisture and concentrating it down here. It's kind of starving this area that seems best for moisture. You can see that really good moisture doesn't seem in this model to really make it all the way up to I-70. Makes it a little farther south. I can keep going, and here go the new thunderstorms, really eating up that moisture. You can see them digging a big hole in the middle of it. And so I see that initiation here kind of down a bit farther into Kansas. And so this is probably going to turn out to be my target based on this model. And I can check that by looking at this model's composite reflectivity and seeing, okay, what's it actually show happening? So this is a completely different model than we've been looking at. This is a WRF model, experimental model. Shows a really nice complex of thunderstorms, again moving through the metro area. Here this is a little later in the day, but not terribly later. It's still like noonish. It moves out, and then voila, there goes those thunderstorms. And they stay messing a complex, but whatever. And they actually move through about north before turning into a nice mesoscale convective system, bow-echo, quasi-linear system, whatever you want to call this, MCS. And this will probably be when the tornado threat starts to diminish a little bit and we turn to more of a hail and wind threat. And that should come through the Kansas City area according to this model, about 3Z or 9 p.m. So as you can see, there's a lot of model variance in here. There's nothing really like conclusive saying, no, just go here or go there. Like there's no just easy map of that. But, you know, we kind of have to work together with all those models, and it's a bit of an art. So let's, you know, just process everything together here for 30 seconds and see where we end up. So I'm going to pull up a map, see what's in that area. And we know, okay, here we are in Kansas City. And let's move a little bit to the west. Okay, here's Topeka. Zoom out a bit more, and here we go. Here's Salina, which I always said somewhere between Salina and Wichita, maybe a little bit to the west. And so the first thing that comes up is this town of Marion, or Cottonwood Falls. Now, and here's the Flint Hills, very hard to chase in here. On the other hand, this area near McPherson has a really nice highway 15 that goes north-south. There's 77 here, so I kind of might say my southern boundary might be this Highway 56 / Highway 4. And this gives me lots of northern routes to chase the storms along here. So maybe saying my starting location might be a Salina or McPherson or Marion, one of this area kind of in here. Understanding that this area up here is certainly easier to chase in, but if we don't have moisture, these storms aren't going to work. You know, a quick sample of this area. Suggest it's pretty flat, pretty easy chasing. Of course, I'm on a gravel road here, which is no good. But that's for more field-based things. So that's kind of how we'll do it, and we'll check it against the SPC, and, you know, in the morning we'll see what the thunderstorms are and what the weather balloons say and how high-resolution modeling works. But for me here, 12 to 15 hours before I'm going to actually probably start putting myself into motion and what I'm feeling. So let's say McPherson, Kansas is a nice target, and we'll work from there.